So now that we've seen how ionic compounds form, and again, our binary ionic compounds, the simplest types of compounds, where electrons are essentially transferred from a metal to a nonmetal, we're now going to take a look at another way in which the elements can become more stable, and this is by sharing electrons in what's known as covalent bonding and the resulting molecules. Okay, so when we talk about covalent bondings, what we are referring to here is the sharing of electrons between elements. And these elements tend to be non-metal elements. Okay, so this is one important difference that generally we'll see. Ionic bonding is typically between a metal and a non-metal. Covalent bonding is going to be between non-metals. And the reason behind this, again, is stability. Okay, this is just another way by which the elements can become more stable. Okay, in order to become more stable, they want to have their valence shell filled. So filled valence shell, just like the nearest noble gas. And this type of bonding can accomplish that by sharing electrons rather than transferring electrons. This type of bonding, covalent bonding, is sometimes referred to as the Lewis theory of bonding, named after Gilbert Lewis. We talked about Lewis dot symbols before. This all ties into that whole theory of bonding. So for example, if you have a hydrogen atom with its one valence electron and another hydrogen atom with its one valence electron, well, the closest noble gas to hydrogen is helium, which has two valence electrons. So what could theoretically happen here is that these two hydrogens can help each other out by sharing a pair of electrons between them. So we end up now with hydrogen connected to another hydrogen via this line. And that line there, that single line, represents what's known as a single covalent bond. And what that means, so what that means in that single covalent bond is that two electrons are shared. Okay, and we represent that with just a line, a single line between the elements. So we're sharing electrons, specifically we're sharing pairs of electrons, right? So one pair of electrons that are shared. And by doing this, each of those atoms become more stable. And I can think of another example. Okay, so if you have something like fluorine with 7 valence electrons, because it is in group 7, I put those in. If I have another fluorine floating around, so 1, 2, 3, 4, 5, 6, 7. We saw before that fluorine can actually take an electron from something that wants to give it up like a metal. Well, if I actually have these two fluorines close to each other, they would actually want to share a pair of electrons between them instead of one losing and one gaining an electron. So we end up forming something very similar. We have F now connected to another F via that single covalent bond. We have these remaining electrons around each of the Fs to make sure that they have a total of 8 electrons around them. So you can think of this fluorine on the left side here as having 2, 4, 6, and then those two that it's sharing are its as well. So it's got 8. And then the fluorine on the right side also has 2, 4, 6, and then it's sharing those two so it can belong to it as well. Okay, so they've adopted their Phil valence shell to be like the nearest noble gas, neon, and as a result, they are more stable. So when this happens, what actually occurs now is that if you think of hydrogen, because the H's are more stable when they are connected to each other, hydrogen actually exists as H2, not as H. Under normal circumstances, right, the hydrogen in the air, for instance, is H2. Similarly, fluorine exists naturally, not as F, but as F2. And there are several elements that occur that way because of the fact that they're more stable when they're sharing those electrons. So when we combine two or more atoms held together by these sharing of electrons, we refer to those as molecules. Okay, so we use the term molecule. Okay, molecules refers to covalent compounds where electrons are shared. Okay, we don't use molecules for ionic compounds. Okay, so for example, if you have sodium chloride, right, which you know is an ionic compound now, we don't say a molecule of sodium chloride. That's not the correct terminology because, as we've seen before, sodium chloride, NaCl, this is the smallest ratio of Na plus to Cl minus. We actually don't have just one Na and Cl. We have millions and billions of them, right? But the smallest ratio is 1 to 1. So we refer to this here for ionic compounds. We refer to it as a formula unit, okay, which is the simplest ratio, the smallest whole number ratio. This is just for your ionic compounds. For covalent compounds, we do use the word molecule, right? That's the simplest unit of that combination, right? So molecules, we have an F2 molecule, oxygen molecule, etc. Versus ionic compounds where we have formula units. That's the terminology that we use. So your molecules then may actually, or they can be elements, or they can be compounds, right? So we know elements are made up of just one type of atom. And we've actually just talked about two examples of molecules that are elements. So for instance, we have H2 that we just talked about. That's an element, okay, because it is made up of one type of atom, which is hydrogen, and it is also a molecule, sorry. So we can refer to this then as a molecular element because it is a molecule, as we just defined, and it's also an element, meaning that it's made up of one type of atom. The other example we saw up here, the F2, the fluorine, right? That's also a molecular element. We have other example, oxygen, for example, nitrogen, N2. We have bromine. We have chlorine. We have iodine. All of these are examples of molecular elements. So in addition to that, your molecules can also be compounds. And we saw an example of this at the very beginning of this section where we have two or more different types of elements. A very simple example of this would be H2O, water, where we have two hydrogens and an oxygen. This would be a molecular compound or a covalent compound. So when we have our covalent compounds or covalent molecules, what has been observed is that when we have different samples of a particular compound, so whether we have, a kilogram of a particular compound or a gram of it, what we've found experimentally is that those different samples actually contain the same elements in the same ratio, the same mass ratio, for example. And this observation, this thing that has always been observed, is known as the law of definite proportions. And this is a law that was originally proposed by Joseph Proust. So Proust's law of definite proportions, we'll see another one in a little bit. So for example, if we have something like carbon dioxide, so CO2, okay, so we have, we breathe this out all the time. If we have 123 grams of carbon dioxide, we can experimentally determine the mass of oxygen in it, mass of carbon in it. And then if we compare, or if we calculate the ratio of the grams of oxygen to the grams of carbon in CO2, and 123 grams of CO2, we find it's 2.66 to 1. If we have a different sample size of carbon dioxide, let's say 50.5 grams of it, and we measure the mass of oxygen, mass of carbon, and we find the ratio of the mass of oxygen to carbon, we find that that ratio is the same. Okay, and this is what the law of definite proportion says. The ratio of the masses of the elements to each other in a sample of a substance is always going to be the same, regardless of what size sample you have. Now, what Proust also determined was that if you had two elements and you can actually combine them in different ratios to form different compounds, what he found was that the ratio of the masses of one element that combines with a fixed mass of the other element in a compound can be expressed in a small whole number. And this is known as the law of multiple proportions. So now we're looking at comparing different compounds. So for instance, if we have carbon, we saw before carbon can combine with oxygen to form carbon dioxide. It can also combine with oxygen in a different ratio to form carbon monoxide, which is CO. And we can do the same thing for the CO down here. If you have 16.3 grams of it, measure the mass of oxygen and carbon, find that ratio of grams of oxygen to grams of carbon. Here we see that it's 1.33 to 1. So what the law of multiple proportion says that if I compare now the grams of oxygen to every gram of carbon in CO to CO2, that ratio then becomes 2.66 to 1.33. And guess what? That is a 2 to 1 ratio. Okay, and that is what the law of multiple proportion says. If we compare the mass of an element to a fixed mass of another element in a compound, to the same ratio in a different combination that for a different compound, that ratio is always going to be a small whole number. In this case, it's a 2 to 1 ratio. Okay, and you can apply that to any combination of elements where different compounds can be formed. So we've seen covalent bonding, the sharing of electrons, typically between nonmetals. We use the term molecules to refer to these types of compounds. They represent discrete entities of the combinations. Okay, we should probably write that down. So molecules. Okay, these are distinct or discrete entities of a covalent compound. And these molecules can come in a whole host of different combinations and different uh, categories. We have what are known as diatomic molecules. Okay, diatomic here meaning di meaning two. So two atoms in a molecule. This means diatomic. And these diatomic molecules can come in also two different varieties. We have what are known as homonuclear versus heteronuclear. The difference there is whether the atoms are the same. So homonuclear, diatomic means that the atoms are the same, whereas in heteronuclear, the atoms are different. Okay, and we've seen several examples of these already. So for example, homonuclear diatomic molecules would be things like hydrogen, we have nitrogen, we have oxygen, what else do we have? Fluorine, we have chlorine, we have bromine, and we have iodine. Okay, and there are 7 of these homonuclear diatomic molecules, which are also elements because they're made up of the same types of atoms. And if we look at the periodic table, we can actually quickly determine, or we can use the periodic table to help us determine this, and I'll show you how to. So on your periodic table, those 7 diatomic elements actually form a nice little shape here on your table. So we talked about hydrogen. okay, occurring in the form of H2. There's also nitrogen, oxygen, fluorine, and chlorine, bromine, and iodine, right? These all occur as homonuclear diatomic elements, molecules. Okay, and if you were to outline their shape where they occur on the periodic table, you will see that they kind of form a shape that looks like a 7. Okay, and there are 7 of them. There are 6 over on this side, right? The nitrogen N2, oxygen O2, F2, Cl2, Br2, I2, and then the hydrogen is over on this side, H2. So there are 7 diatomic elements on the periodic table. Okay, and you need to know those because that's the way that they exist under normal circumstances as combinations rather than individual. Heteronuclear diatomic elements, these are where the atoms are different. So for example, we can have something like HCl, we can have CO, carbon monoxide, for example. So they're different in that case. We can also have polyatomic molecules. Okay, these are ones that contain more than 2 atoms. Okay, so for example, something like CO2, right, um, would have 3 atoms in it. Something like H2O would also have 3. You have lots of other examples as well. So when we represent our formulas for our compounds, there are several different ways by which formulas can be represented. We're going to touch on a few of them right now. We have what are known as chemical formulas, and we've been dealing with chemical formulas all up until this point, right? They give us the ratio of the elements to each other. So for example, H2O would be an example of the chemical formula for water. The molecular formula is kind of interchangeable with the chemical formula. This is going to show us the exact number of atoms in each element in the molecule. So again, for H2O, it would be the same. Right? It would also be H2O in this case. Some elements, they actually exist in different forms under normal conditions. So when you have elements that have 2 or more distinct forms, we refer to these as allotropes. And now this is in contrast to isotopes that we saw earlier on. Okay, it's important to note the difference between them. An allotrope would be an element or different form for an element. So for instance, oxygen can occur as normal O2 that we breathe in, but higher up in the atmosphere, oxygen can occur as ozone, which is O3. Okay, so those are different forms of oxygen, the element, either O2 or O3. Another example here would be something like carbon. Okay, carbon can exist under normal conditions either as graphite, okay, which is in your pencils, or it can occur as diamond, which is not in your pencils. You wouldn't want a pencil made out of diamond. It would cost you way too much. Similarly, you wouldn't want a diamond ring or a ring made out of graphite. Well, maybe you would, I don't know. But they're very different, even though they're both made up of the same element, carbon. It has to do with how the atoms are connected to each other. So those are allotropes. And here, the allotropes of carbon. There are many other allotropes of carbon. These are just the 2 most common ones. The structural formula, the last one here, this not only gives us the elemental composition, the different types of atoms, but it also shows us how the atoms are arranged. Okay, so for example, if I look at water, okay, water has a chemical formula H2O, gives us the ratio of the atoms to each other. This is also the molecular formula. This doesn't tell me how the atoms are connected. How they're connected is known as a structural formula. And for water, water actually looks like this. So there's an oxygen connected to 2 hydrogens on either side, and we have 4 more electrons around that oxygen to make sure that it's happy with its octet. Okay, so this is known as a structural formula. We will draw structures a lot in the next section. So when you see these models in your textbook, you will get used to the different color schemes, just so that you know the most common ones that we will encounter. Hydrogen is always white, carbon is always black, and oxygen is always red. The other ones, you'll eventually get used to these, but those are the three most common ones that you are going to see with your structural formulas, right? So structural formulas, how the atoms are connected, the structure, in other words. The last type of formula that we'll take a look at here is known as the empirical formula. And the empirical formula, what it is, we've also addressed this a couple of times already. Empirical formula is nothing more than the simplest whole number ratio, or the simplest or the smallest whole number ratio of the elements to each other. And we've already talked about empirical formulas being used for ionic compounds. Okay, so for your ionic compounds, this is what we want. We want the empirical formula, the simplest whole number ratio. We're going to use the empirical formulas. Okay, again, for example, sodium chloride, right, is a 1-to-1 ratio. You never have just one sodium to one chloride in sodium chloride and table salt. You have billions of one, but you also have the same number of the other. Okay, and it would be impossible to write a formula that wouldn't be impossible. It would be very cumbersome to write a formula like that. So we represent it as the smallest whole number ratio where those charges cancel out. Okay. Now for your molecular formulas, which we know now we use for covalent compounds, they're going to be more informative than the empirical formula. So for example, if we have something like we have a covalent compound, and we'll do hydrogen peroxide. So hydrogen peroxide has the chemical formula H2O2. Okay, this is the molecular formula for this. Okay, which tells us that in this sample of hydrogen peroxide, we have discrete units of 2 hydrogens and 2 oxygens combined together in whatever structure that they are going to combine in. Okay, so for example, if you were to draw that out, it would look something like this. So hydrogen peroxide is made up of these discrete molecules. That is the molecular formula, H2O2. It tells us exactly how many atoms are there. We can simplify this, however. We can get a smaller whole number ratio. We just divide both of these by the smaller of the two numbers, which is 2 in this case. So this then becomes HO, and then this is your empirical formula. Okay, you will note that hydrogen peroxide is not made up of one O and one H, right? It's actually made up of 2 O's and 2 H's in that ratio, right? So for covalent compounds, the molecular formula is going to be way more beneficial for us than the empirical formula would. But just so that you know, the empirical formula is just the simplified version of a molecular formula, right? The simplest whole number ratio. We can take a look at a very good example down here. We'll do this off to the side. If we have something like glucose, okay, glucose has the chemical formula, molecular formula, C6H12O6. So glucose, which is a type of sugar, is made up of 6 carbons, 12 hydrogens, and 6 oxygens. This is the molecular formula. I'm going to abbreviate that. We can simplify this and we can come up with the empirical formula by dividing all of the subscripts by the smallest out of the subscripts, which is 6 in this case. So if I divide all of these by 6, I end up with C1H2O1, which is the same as CH2O, right? This is not what glucose is, right? Because we just said glucose has 6 carbons, 12 hydrogens, and 6 O's, but this is the simplest ratio of those elements to each other. All right, when you eat something that has glucose in it, this is the formula of the molecule that you're eating, not CH2O. Right? This is just the smallest ratio. So it's important to know the difference between those two.